Brilliant, great. Okay, well, first of all, welcome everyone and thank you for coming. This is now the 11th seminar of the Cambridge Disaster Research Network. If you're joining for the first time, I'm Rory. I'm one of the early career postdoc conveners of the network. And the network itself aims to connect people interested in disaster research, not just across the University of Cambridge, but also wider for those outside of Cambridge. And today's session is on the topic of planetary defense and disasters from space. And we're lucky to have three excellent speakers on this topic. Our first speaker is Lindley Johnson. Lindley is NASA's Planetary Defense Officer and Program Executive of the Planetary Defense Coordination Office. Our second speaker is Dr. Patrick Michel, Research Director at CNRS, the French National Centre for Scientific Research. He's also the Principal Investigator of the HERA project at the European Space Agency. And thirdly, we have Leviticus L.A. Lewis. LA works for FEMA, the Federal Emergency Management Agency in the United States. And he's working with the White House Office for Science and Technology Policy and the NASA Planetary Defense Coordination Office. So those are our three speakers. And the structure today is that each speaker is going to talk for about 12 or 13 minutes in that same order. So Lindley, Patrick, and then LA. And then we'll have a discussion and Q&A at the end. So please save your questions to the end. One last thing to say is a big thank you to Dr. Laura Manny of CESA, who suggested this topic and this session and helped organize the whole thing, which is exactly what we wanted for this network, to sort of generate discussions and also to produce new connections and new interesting topics and seminars for the community. So without any further ado, I'm going to hand over to our first speaker. Over to you, Lindley.
Okay, thank you, Rory. I'm going to turn off my video here, make sure the bandwidth stays up. And at NASA, we got to send our signals about 3 times around the Earth, and it's got to come back down. So sometimes you can lose us. So hopefully you see my first slide here now. Okay, very good. I'm going to stay in this mode because of some issues we have. It's a pleasure to be here and talk with you. Thanks for your invitation. Try to give you a very quick rundown about planetary defense. A little difficult to do in 12 minutes, but we'll do our best here. Okay, now my slides are not. This is interesting. Oh, there we go. Okay, well, planetary defense at NASA, this is kind of our strategy. You read it like a clock. Up in the upper right, our highest priority is to search, detect, and track objects, near-Earth objects, asteroids, and comets that can come near the Earth. So a good deal of our effort is concentrated in that area. Then we have a lot of projects whose job it is to characterize these objects so we understand them better, what their size and composition might be, and if they could represent an impact hazard to the Earth, have some idea about what we would be facing, first of all, if they were to impact, what the effects would be, so we could advise on that. But also, hopefully we find them far enough ahead of time that we could do some kind of in-space mitigation measure. And so we need to understand as much as we can about them. So we have a number of projects and systems that are working to better characterize the objects. We are the Planetary Defense Coordination Office at NASA. If we were to face such a international emergency, asteroids don't respect national borders, we would have a lot of planning and coordination that would need to be done to mount a effective response to preventing such a disaster. And so we are involved today in a number of efforts coordinating what our response might be, both within the United States and internationally with several different organizations, as you see here today. Then, of course, the part that everybody likes to talk about, mitigation, and both in-space mitigation, which we hope we find them fast enough or far enough ahead of time that we could do something in space to deflect the asteroid, and also demonstrating techniques to be able to do that, but also working with the emergency response community and FEMA here in the U.S. To exercise providing as much information and data as we can to enable them to have a effective response here on the ground. And then, of course, we need to be able to assess all of our capabilities. Are we finding them fast enough? Are we adequately characterizing, and so on? As I said, we work with an international community of things that negotiations that were set up underneath the Committee on Peaceful Uses of Outer Space, and where it was agreed and endorsed by the United Nations General Assembly. Two entities, these are not UN entities, they are international collaborative efforts between the astronomic and space communities, Space Institute communities around the world. First of all, an International Asteroid Warning Network, which would, first of all, find them and then determine any potential impact, where that might be and how severe it might be. And that effort is coordinated by NASA, Planetary Defense Coordination Office. The other entity that's in existence is called the Space Missions Planning Advisory Group. This is a forum for the national space agencies around the world to join on collaborative efforts on techniques and technology that might be used to deflect an asteroid in space, and collaborate on these projects, and then be able to recommend to the national space agencies and the international community, should an impact threat be found, what might be the best options for a response to that if it could be deflected in space. The Space Missions Planning Advisory Group, which called the same page, get everybody on the same page. The International Asteroid Warning Network, as I said, has observatories, space institutes around the world join the effort to detect, track, and characterize these objects. There are currently, well, I think 32 is actually a little short. I think we've had a few additions since this slide was just made a couple of months ago. But you see ranges from the national space agencies like NASA and ESA, the European Southern Observatory, and also we have several, I hate to call them amateurs, really call them pro-ams, quite capable amateur astronomers around the world with some pretty sophisticated telescopes that also provide us observations once these objects have been detected by our major survey, so that we're able to better determine their orbits and project out into the future when might one present a hazard of impact in the Earth. Our current catalog of near-Earth asteroids, well, we just broke through 25,000 here in February. And as you see there on the right, we're about to cross 26,000 near-Earth asteroids of all sizes. Now, the vast majority of those that we are finding now are smaller ones, smaller than this 140-meter size. Size threshold was established by our Congress as to the population of objects that they wanted us to find and have a good handle on of their orbits to determine whether there could be really a significant impact hazard to the Earth lying out there into the future. So there's 140 meter and larger, and those that come within about 5 million miles, 7.5 million kilometers of Earth are considered the potentially hazardous objects, ones that we truly need to monitor. And we're almost at 2,200 of those objects. There are also in our catalog almost 900 asteroids 1 kilometer and larger, and of course we don't want to get hit by one of those. 157 of those are of this potentially hazardous coming within 7.5 million kilometers of the Earth. And we also have a little over 100 comets that also approach the Earth within 30 million miles. So our progress on finding this population of potentially hazardous asteroids, our modeling of what could be out there based on what we've found so far estimates the total population could be as high as 25,000. And the status of our survey as of this last year was we still have about 60% of those to find. About 7% of that is objects that are 300 to a kilometer in size. We've already found virtually all of the 1 kilometer and larger population, just a small percentage of those yet to find. So the vast majority are smaller than 300 meters in size, and that is a bit of a challenge with our current systems. At the current discovery rate, it's going to take another 30 years, even though we've been at this for 20 years now, to find that complete population of 140 meters and larger. So our answer to that is a new space-based telescope specifically designed to find the population of near-Earth objects. This is the first time that there has been a space-based telescope designed to do this job. It operates in the infrared. These objects are easier to detect in the infrared against the background of stars. And that infrared signature that we collect as we detect and track these objects also allows us to make a good estimate of their sizes. So we will have an idea of what we're really looking at as these objects are detected. Whereas ground-based observatories operating in the optical wavebands, the range and size can vary quite a bit because the reflectivity can vary quite a bit from the surface of these objects. And a lot of them are quite dark as charcoal. So they are hard to see in the optical, but in the infrared, they absorb and re-radiate the sunlight and are just as easy to detect no matter what the size is. So this near-Earth object surveillance mission, it's been a concept in development for a number of years. And we have just been approved to enter a preliminary design here this year, which means we will be about 4 years, 5 years away from launch. And the other good news is that the president's budget request that was released just last week provides the funding for this mission to go forward. So next step is Congress to approve that budget. Looking more at mitigation and what the risk could be of impact, we have what we call our asteroid impact threat assessment modeling work that's done by our Ames research group, led by our Ames research group, I should say, because it involves models from a number of different U.S. government agencies, Department of Energy, Department of Defense, and NOAA, that based upon what we see from our observatories in space and are able to detect and track and characterize, that is then used to model what the effects might be of an asteroid entering the Earth's atmosphere. Is it big enough to withstand the pressure and heat passing through the atmosphere and cause damage at the ground? And then modeling what those effects might be, both blast and thermal, that could affect an area and the population anywhere on the surface of the Earth. So this modeling goes all into our impact threat assessment work. And most recently, you may have seen in the news of the impact emergency response exercise that was done as part of the 7th International Planetary Defense Conference, which was just a month ago, end of April, where we had a impact exercise projecting an impact of a 100-meter sized asteroid tracked in and determined toward the end that it was going to impact in Central Europe. And so this is the modeling of what we could say about that about 6 days prior to the impact, after both optical and radar tracking from our current systems. This particular object would have entered the Earth's atmosphere at about 15 kilometers per second. And at that size, the energy release could have been on the order of 40 megatons. So the area that could be devastated by such an impact might be about 25 kilometers in radius. And the total area affected by an impact of an object this size could be as much as 140,000 square kilometers. So, of course, this is not something we want to happen. And so we want to find these in space, find them early so that we have time to do an in-space mitigation technique. Viable techniques that have been studied, the kinetic impactor, gravity tractor, and then, of course, the Hollywood solution, the nuclear explosive device. But all these work on the principle that we only need to change the velocity of the asteroid by a few kilometers per second if we do that several years in advance. So if we're able to find an object at least 5, hopefully 10 years in advance, which is entirely possible with the technology we have, and particularly this IR telescope I talked about, we then have the opportunity to use these techniques to deflect the asteroid off of an impact trajectory. And what we are doing in that now, we have a project called the Double Asteroid Redirection Test, or DART. It is in its final integration and test, and it will demonstrate the kinetic impact or deflection on a binary asteroid called Didymos. It was scheduled to launch here in just 2 months, but because of the pandemic effects on slowing down some of the final development of some of the elements like the solar arrays and the Draco imaging camera, we've had to slip the launch now to the end of November 2021. But now 6 months, but only 6 months from launch, and it will still impact the moon called Dimorphos of the Didymos system in September. This is all part of a international collaborative effort called the Asteroid Impact Deflection Assessment, which Patrick is a part of. And so here I'll talk to you about this a little bit more, and the European Space Agency's HERA mission.
Perfect. Thank you so much, Lindley. Just if anyone's coming in late, we're saving our questions to the end. So over to Patrick.
Okay, thank you, Lindley. You see my screen?
Yeah.
Okay. Okay, so thank you very much. So effectively, I'm going to talk to you about the DART and HERA missions, which constitute the first complete test of asteroid deflection. So I won't go into all the other deflection techniques rather than the kinetic impactor technique that will be tested by a lack of time. And actually, we have a real mission going to test this technique. So I think it's worth to describe what's going on this topic. So in fact, all started at ESA in the early 2000s, when a few colleagues and myself actually recommended as a first mission to address the impact risk, the kinetic impactor technique, with a mission that was called at the epoch Don Quixote, and which involved 2 spacecraft, one being the projectile and the other one being the orbiter that will observe the outcome of the impact and measure the deflection. But then there was no program dedicated to this topic at ESA, and therefore no budget, and it went into the desks, and eventually, fortunately, gave birth to a new framework, which is this IDA international collaboration. So IDA stands for Asteroid Impact and Deflection Assessment, which is a collaboration that supports the development of the DART mission by NASA and the HERA mission by ESA. So as Lindley said, DART will launch in November this year and will make an impact in fall 2022 on the small moon of the binary asteroid Didymos. So the small moon is called Dimorphos. And before doing so, it will release a CubeSat called LISHA-Cube that will observe the first instant after the impact. It's developed by the Italian Space Agency. And then HERA will come on the crime scene a few years later to fully characterize the outcome of the DART impact, as well as the target itself, because we need, in order to really understand what happened, to have a fully documented impact experiment, which include both the initial condition provided by DART and the final outcome provided by HERA. So as I said, DART will make this first asteroid deflection test. So that's really great because there are many techniques that work on paper, but we need to test to make sure that we control well the techniques and we validate it. The launch, as I said, will be November, and Lindley showed this diagram showing the impact of the DART spacecraft, about 600 kilograms at arrival, between 530 and 600 kilograms at arrival, and impact speed at about 6 kilometers per second. And then it will basically perturb the orbital period of Dimorphos around Didymos. And what's great is that because it will happen when Didymos pass close to the Earth, we can even measure from ground-based observatory the change in the orbital period of Dimorphos around Didymos, which is a first kind of measurement of the deflection. So this is a DART spacecraft, which has an imager and a guidance, autonomous guidance to make sure that Dimorphos is reached. And this is a very challenging because for now, we don't even know the shape of Dimorphos. We have a shape model for Didymos, the main object, but not for Dimorphos. So basically, there will be an automatic recognition knowing that it is going at 6 kilometers per second. This is something that we need to test. And in fact, if I show you Dimorphos compared to other monuments that we are very familiar with, you can see that it is very, very small. So we are really looking at a very challenging target for which we know not much except for the primary, and which is good because as a test, a blind test, if basically it works as expected, shows that even when we don't know much, we know what we do. So that would be that increase the confidence, I would say, rather than if we knew everything from the start. It's easier, of course. So what we want to measure actually, it's the momentum transfer efficiency. So basically, when you impact an asteroid, you transfer the momentum of the projectile. And then if you emit some ejecta, by conservation, the momentum carried by the ejecta in the opposite direction of the impact add to the momentum of the projectile. So in other words, if you don't have any ejecta, the only momentum that the target have is the momentum of the projectile. If you have ejecta, then of course you add and therefore you deflect better. So the more ejecta you have, the more deflection you achieve. And of course, all these depend on the structure of the asteroid, of its response to the impact that we don't know in advance. And in order to measure what we call this beta factor, which tells you how much enhancement of the momentum we achieved, you need to know the mass of Dimorphos, which comes into the equation. And this is where HERA comes, you will see. So DART by itself has some requirements. First is to impact Dimorphos, of course, then to change the binary orbital period, then to measure the period change with ground-based observations, and then to have a sort of measurement of this beta factor, which will not be direct, but with modeling and knowing the change orbital period, you can at least get the first idea of how much is the enhancement of the momentum that was transferred to the target. So HERA will launch in October 2024 with an Ariane 6, and will arrive at Didymos at the end of 2026. And then there will be a few months of close proximity operations that will allow us to fully characterize in great detail the outcome of the DART impact, as well as the target itself. So we arrive 4 years later, but it's not a problem because basically the thing that we need to measure won't change over such a short period astronomically. So HERA spacecraft is developed by OHB Industry as a prime. There are many subcontractors, and it carries several payloads like asteroid framing cameras, a LiDAR, a thermal infrared imager, which is provided by JAXA. So we have a Japanese component. It's really an international collaboration with DART on the US side, Italians with the Lisha Cube, and then HERA with a Japanese component, a hyperspectral imager, and then 2 CubeSats with different goals. One is devoted to the internal structure, which has never been done before, with a low frequency radar. You can see the antenna here. And then another one, which is devoted to the mineralogy and also the detection of dust around the asteroid. So in fact, it's very fascinating because we need to characterize better these objects because, of course, as I said, the way that we react to an external actions highly depends on their properties. And what we discovered, thanks to the past space mission, and in particular, the most recent ones, OSIRIS-REx by NASA on Bennu and Hayabu 2 by JAXA on Ryugu, is that we deal with an incredibly diverse population in terms of geophysical properties and composition. And even better, on one asteroid, you have a great diversity in terms of rock morphologies and geological features like landslides, troughs, etc. So it's really fascinating because when you go to see a new object, you feel like an explorer of a new territory, which actually evolve in a very different condition than the Earth. And therefore, it's very difficult to really intuitively understand them. You need to explore, you need to interact with them. And that's what OSIRIS-REx Hayabu did, and that's what DART will do with HERA. So HERA will have a lot of first actually, because even though it's focused on planetary defense, there will be a lot of science return because we never made a rendezvous with a binary asteroid, for instance. So there will be flybys of binaries by a Janus mission, which is in the Simplex program of NASA. But here we'll make a real rendezvous. And then we will characterize a very small object, 160 meters in size, which we can compare with Otoeme Saxum on Ryugu, which is about the same size, but we don't know what it means to be 160 meters in size free in space. What are the properties? It's very intriguing. Then we'll have the first radar sounding. So for the first time, we will have a direct measurement of the subsurface and internal properties. This is something that has never been done. The only thing that we know usually is the bulk density of the object that you compare with meteorite analogs, and the difference give you the amount of porosity in the object. First, you need to make sure that the analog is correct, and then what we mean by porosity is never clear. So here we have a first way to probe directly inside, which is really exciting. And of course, with DART, we'll have a fully documented impact experiment at asteroid scale. And even scientifically, it's very interesting because the impact speed of DART is 6 kilometers per second, which is about the average speed between asteroids. So you can also understand asteroid collisions by this effort. So what we want to do with HERA is first to measure the mass of Dimorphos, because as I said, it goes into the equations of how much you deflect. And to do that, it's very challenging because Dimorphos is very small compared to Didymos. It's maybe less than 1% of the mass. So you have to come very close in order to feel some perturbation, or you need to use some tricks, like the fact that there is a wobble, and by measuring the wobble, you can actually access the mass of Dimorphos. Then what is very interesting is that Dimorphos is, as I said, in a very interesting size range. This is the spin period as a function of diameter of the asteroids. And you can easily identify two regimes. When asteroids are big, basically when their centrifugal force exceeds their gravity, they cannot survive. And therefore, they have a limit in their spin rate due to this excess of centrifugal force compared to gravity. So, which means that they are dominated by their gravity. Then at the small size, they can start to have cohesion. And in that case, they can spin faster. Dimorphos, interestingly, is in the transition size between the two regimes. So based on these spin period, basically, we cannot know in which way it will react, whether it has strength, whether it is dominated by gravity. So that's very interesting because that will have a lot of implication on our understanding of asteroid geophysics and on the impact response with DART. Will it react like a gravity-dominated body or a strength-dominated body? We don't know. And target properties are very important, and this beta factor does not provide the full answer. These are some simulations of impact that show you different crater morphologies, which we achieve for the same efficiency of momentum transfer. So for the same beta. But you can see that with beta and the crater morphology, then you can relate to the target properties, because these are the target properties that drive the crater morphology. So if you have the crater size if you have radar sounding, and if you have beta, then you have your target, which is fully documented, and therefore your impact experiment, which is fully documented, including impact conditions, impact outcome, and the target properties. And that's very important because this is how we can validate the numerical simulations, which have to reproduce the DART impact. They need to start with the correct parameters and the one that correspond to the target. And that's very important because so far, the way we validate the models are with doing lab scale experiments. Basically, you take centimeter size targets, you put them in the two-stage light gas gun, you impact at 5 kilometers per second, and you compare with the simulations. But we know that the extrapolation to large sizes is highly uncertain. And why good demonstration is the Hayabu 2 impact experiment. The Japanese mission made an impact experiment carrying a 2-kilogram projectile launched at 2 kilometers per second on the surface of the asteroid Hayabu. That was super risky and super successful. And basically, you can see here the movie made by a small camera of the impact itself. And one surprise was that you have a lot of ejecta falling back on the surface. And the escape speed of the body is only 20 centimeters per second. So when you shoot at 2 kilometers per second, you expect that the material will fly away at much larger speed than 20 centimeters per second. And yet, we see a lot of them coming back, which is a first surprise. The second one was that the crater is much larger than we expected if the surface had cohesion. So the only way to explain this large crater is if the surface has no cohesion, which is still surprising. So the bottom line is that we still have a hard time to understand how these bodies behave in their low gravity environment and how they respond to this kind of impact physics. So we need to experiment at the correct scale in order to verify whether our models are able to capture these conditions. And that's what we do with DART and HERA. And that was on Ryugu, a 900 meter at 2 kilometer body at 2 kilometers per second. Now we'll see how it goes when we go smaller in size and at higher speed. And finally, in terms of low speed of impact, we'll also make low speed impact, hopefully, of our CubeSats on Dimorphos. And that will allow us to measure the bouncing coefficients and therefore to have other information on the mechanical properties of the asteroids, which are always important for planetary defense and other purposes. And we now know that the only way to really understand the mechanical properties is by a direct interaction because they react very counterintuitively. We saw that with OSIRIS-REx and Itaxan that basically went through the asteroid with no reaction, and on Hayabu 2 with a small carrier impactor. Based on what we see on the surface, it's very hard to capture whether the body is soft, has no resistance, or whether it's hard. We really need to experiment. So we will have two different kinds of interactions. And finally, we will also investigate a body which is at the limit of disruption because the main body of Dimorphos is rotating at 2.26 hours. And we did some modeling of its evolution. And we find that it cannot exist in its current state if it doesn't have cohesion. However, even a small amount of cohesion is enough for him to remain at this state. So we are really dealing with a body which is at the margin of stability between something that is moving and something that is stable. So it will be really interesting to see how this behaves and to understand binary formation because 15% of asteroids are binary. So it's in a non-negligible fraction. Some of them could be threatening, so we need to investigate more. So in conclusion, DART and HERA have a lot of first deflection, first rendezvous, first deep space CubeSats for very close asteroid impaction, and first internal structure probing. So that's all very exciting, and we expect a lot of surprise. And as I always say, asteroids are fascinating because they are of high interest for different communities, which have very different purposes, from science to planetary defense to even mining. But in fact, they essentially need the same knowledge at the level where we are now. So that's great because whichever the primary objective of your mission, you will feed these communities with the knowledge that you get. And DART and HERA are also, of course, fascinating because, as I said, we'll do a first deflection test. Hopefully it will work and we'll be able to validate and improve our modeling that we can extrapolate to other scenarios. And for Europe, it's the European contribution to planetary defense. We also have the European Commission that funds some consortia to support the development of HERA. So it's really great. And then we also have a great team and community. to this IDA consortium. With the DART team, we have an excellent atmosphere to work. And that's very important because that's a way to promise amazing discoveries and contribute to save the planet. So I just show you the team, and I thank you very much.
Wonderful. Thank you, Patrick. That was really excellent. And now to hand over to our last speaker, LA. Over to you. You're just on mute at the moment, LA.
Okay, can you hear me now?
Yeah, that's perfect. Thanks.
All right. And I'm going to share my screen here. Okay, can everybody see it?
Yeah, that's brilliant.
Okay, I'll make this really quick. The last two presenters, of course, were fascinating, so mine's going to be pretty quick and boring. But just to let you know, from the ground part, hopefully my esteemed colleagues, the Planetary Defense Corps officer for the U.S. for NASA, Mr. Johnson, and Dr. Michel will save us from having to do anything on the ground. But if it doesn't work, or we run out of time, it'll be over to us and my colleagues and internationally who do emergency response. So just give you an idea, it's a typical organization. I work for FEMA, which is the Federal Emergency Management Agency. I'm actually in the Office of Response and Recovery, and I actually work for the Response Directorate. So we are the boots on the ground who will be going to support this effort directly if our missions fail. So in the United States, and I'm sure this is the same for my international colleagues, there are already established laws and authorities for their emergency responders. Even though I would say I did participate in a seminar yesterday with my European colleagues for ESA and some folks from the EU, the EC and their emergency response organizations. It's going to be a little bit difficult, I think, a little bit more challenging. For at least in the United States, we have a unified response framework, and we have a law that cover all 50 states and all territories. So the same federal authorities that allow us to provide disaster assistance to state and local authorities is the same everywhere. Where I would imagine in other countries that have differences, or every country has their own way of doing it, the challenges of coordination might be a little bit more difficult or challenging. So it's good that we're all working together to mitigate this and know kind of a standard of how we're all going to respond, because this will be an international incident. But for right now, our plan in the United States is the plan for impact in the continental United States or in one of our territories. So our main act is the Robert Stafford Disaster Relief and Emergency Assistance Act. Basically, it's a way for the president to authorize federal aid to states, tribes, and local authorities that are overwhelmed. The idea in the U.S. is that any emergency response is first going to be responded to by the local authorities. A lot of people think that the feds in the United States can tell this town to evacuate. Well, in the United States system, the federal government does not have that authority. That rests with the local authority. And of course, being in the United States, every place has a different way of doing it. So it's very important. But the idea is that we do have a unified way of making sure that we can provide federal resources if those local and state authorities become overwhelmed. And we think that an asteroid impact is going to be a quite different emergency that our citizens are not used to. So we have a couple of main tenets for FEMA: is simplicity and boldness in response. Go as quickly as possible, provide as many resources as possible, and try to make sure that while we're helping, we're not getting in the way. And the singular focus on the outcome is to meet the needs of the survivors. And one of the other things that we've been adding also lately is the community response. One of the ways that we grade success of response here in the U.S. is how soon that local community can get back on its feet and operate on its own without the need for much federal assistance. In this particular scenario, we think that it's going to be a very, very intense effort, and it's going to require national assistance almost immediately, based on what the size of the object is and what's projected to happen. Again, these are just some of the laws. We have a national response framework, and that's a guide to how our nation responds to all disasters and emergencies. everybody operates under the National Incident Management Systems, which gives us a little bit of an advantage to how we respond to this. Everybody knows what to expect from the federal government. We can also judge on what that local community might need. We've done a lot of mapping on where our critical infrastructure is, what's important, what's not important. You will have to come up with a list, making sure with the work that NASA is doing, especially their asteroid impact threat assessment team, that the work that Ames is doing, that's very important to us to have an accurate map of what's population centers, critical infrastructure centers, what needs to be done first, what needs to be done second, how many people need to be evacuated. Of course, we have a lot more experience in this in the United States because we have large populations that are used to evacuating for hurricanes, et cetera, et cetera. The entire East Coast of the U.S., the entire Gulf Coast of the U.S. is already used to having to move on a large scale if something happens. So again, the Stafford Act, don't really need to know that. We have an emergency declaration, a major disaster declaration, and fire management assistance program. These are tools that the president can use to provide assistance in a faster means to the states. The states always request it first, but we do have the authority now. That's a change because of the large Hurricane Katrina and other disasters that's happened to the United States. Before, the law required us to wait for the state governor or local assistant to make an official request for help. But under the new authorities, we can actually start moving rescue teams, supplies, and other equipment to pre-stage and be ready and actually engage them before the event happens. And of course, that's the same with this particular scenario. We'll either get warning or we won't. Or the challenge that our science colleagues have explained to us very well is that there's differences. We could get no warning. We can get minutes. We can get months. We can get weeks, days. And these are those things that require a slightly different response from the emergency management community. But the whole thing would be communicating what's going to be happening to our population, how it works, and what we expect them to do. Again, we have 10 regions. We're divided up into 10 regions in the United States. Each region has their own administrator, and we coordinate. That administrator is responsible for reaching out to all of the states and its regions and making sure that we're all tied, connected with communications. And that's one of the things I'm working with my NASA colleagues on. We are charged with formalizing how we're going to get the word out to all emergency agencies. So just for an example, and I'm sure it's the same in other emergency response organizations and other nations, we make a clear distinction. What FEMA is going to do, you see that on the left, we have certain responsibilities, and then what happens on the right, other agency responsibilities. One of the key things for that you might be interested in is that FEMA has got the responsibility of providing the emergency management advice to the President of the United States. And such one of the things of our authority is that we can engage other federal authorities, other federal agencies to assist in whatever the disaster response is, including the Department of Defense. And we have the financial resources to support those other agencies that might be providing the response. So I think a key thing to remember here in the U.S., we have developed a national near-Earth object preparedness strategy and action plan. It's been signed by both previous administrations, so it's been a large body of work done with this, and I've been working with my colleague, Mr. Lindley Johnson, for the last 10 years on this project, and we have it signed out, and right now we're in the process of actually executing the goals outlined in that national strategy. So our emergency response role in a neo-impact scenarios like this, what you see here on the screen, we're going to use some of our procedures that are already in existence. So we already have a checklist for re-entering space debris, or hurricane warning procedure. So it's going to be a modification of that. We got a test of that a little bit a few weeks ago with the re-entry of the Chinese Long March rocket body. We got to do a little bit of practice of that, keeping everybody calm, because everybody was assisting that was going to impact their area. But we had to explain to everybody how that works, and so we know we do have some practical experience, but an asteroid is going to be a different thing. So we want to make sure that happens now with the advent of the internet and everybody having a camera everybody's seen the films of the Chelyabinsk impact, and people are always surprised when I tell them, hey, that was only like a 17 to 20 meter size object. And if you imagine what a 100-meter object would do, and people pay attention, like, okay, but they always assume that we have a plan. Again, like I said, public information would be very important, how we work with our public affairs personnel. And then the timelines for decision making can vary from years to days or hours. And in each case, the emergency response will be a little bit different. So in summary, what we're going to do is try to stabilize the results for our citizens, and it's a coordinated action of the entire response community, not just from any one organization. And here in the United States, it's federally supported, state managed, but it's always locally executed. So that's our main way of how we attack this scenario. And that's it. Thank you very much.
Perfect. That was excellent. Thank you so much, Ale. So we now move on to the Q&A and discussion.